Okay, so let's discuss the most important problem in PVMP, that is the SAT problem. So, some new terms. Consider we have a set of Boolean variables, x1 through xn, and we say a literal is either a Boolean, that Boolean variable, or its negation, and a clause is a disjunction of literals. So a disjunction is simply means that you have a set that's ORed together. That's all that means. So for instance, the clause here is x1 or x2 or not x4. Okay, each of these are literals, and together they're a disjunction of literals or a clause. Okay, so a formula in conjunctive normal form is is a conjunction of clauses. Okay, so it is a conjunction. It is the anded. It is clauses anded together, and each of these clauses are a disjunction of variables. Okay, so this is the opposite of what's known as disjunctive normal form, which a lot of you, if you've taken computer organization, any sort of circuit, any sort of VLSI, logic design, you would typically get formulas in terms of x1 and x2 or x3 or x4 and x5 and x6 dot dot dot. That this is known as a DNF formula, disjunctive normal form formula. Okay, and that's what circuit designers typically use. Oh, in our case, computer scientists, what's interesting is that when you go from a DNF formula, when you reverse the operations to conjunctive normal form, the problem becomes much harder, much harder, and we'll discuss more about why that is in a moment. So, a CNF. So we talked about what a CNF formula is, and a formula psi is 3CNF if every clause has exactly 3 literals. Okay? So this here is a 3CNF formula, but this here is not a 3CNF formula, but it is still a CNF formula. Okay? The 3 here just literally signifies how many literals are in each clause. Okay, so here's the problem. Let's say the problem, and we define two possible problems. First is the standard SAT problem, i.e., you have a CNF formula. Is there a truth assignment to the variables of psi such that psi evaluates to true? Okay, so for instance, let's say the formula is x1 or x2 or x3 anded with, I don't know, not x1 or not x2 or x3. Or, I don't know. Yeah, let's just do x3. Okay? Is there a truth assignment to these variables, to the variables x1 through x3, that gets you this formula to evaluate to true? And the answer is, of course, yes, there is. For instance, if x1, comma, x2, comma, x3 were equal to 1, 0, 0, then because x1 is 1, this clause would evaluate to true. Because x2 is, because x2, x not x2, this is true in this case because x2 is 0, then this clause evaluates to true, and the ANDed of these two clauses both evaluate to true. Okay, so one thing that's interesting that you should see in the conjunctive normal form is that for each of these clauses, you only need to get one literal to evaluate to true in the clause, but then every single one of the clauses has to evaluate to true in order for all the total formula to be true. Okay, so that's the SAT problem, and then simply the three SAT problem is simply the same thing except each clause has three literals. Okay, so over here I did the example in terms of the three SAT problem, but this three SAT problem is a subset of the SAT problem also. Okay, so for instance, so a few more examples. This formula right here is satisfiable. Why? Because if we have x1 through x5, if we assign it to be equal to, well, we know x5 has to evaluate to 1, so we know that at least. I could go there, 1, or not 4. Okay, I could knock down the first and actually there, and the 1, 1. Okay, so because of this variable, this clause would evaluate to true. Because of this variable, this clause would evaluate to true. And because of this assignment, this clause evaluates to true. And therefore, all these truths added together gives the formula as true. Okay, so definitely there is a assignment, at least one assignment where this formula would evaluate to true, right? And so now you might be thinking, it seems like, I mean, all you need to do is get one of the literals in every clause to evaluate to true. So it seems like it would be pretty easy to get them all to evaluate to true. And I mean, I don't think that's necessarily wrong. I think there are a bunch of SAT solvers in the world that would use this strategy of saying, okay, look at each clause, simply set one of the literals to true, look at the other clause, set another literal to true. It's sort of a greedy approach. SAT solving is a whole algorithms topic in its own. But there are formulas that will not be satisfiable, that will not evaluate to true. And a good example of this is simply this. Okay, no matter what we assign x1 comma x2, one of these clauses would not be satisfied. So for instance, if x1 and x2 are 0, 0, right, then this clause is satisfied, this clause is satisfied, this clause is satisfied, but this clause is not satisfied. Okay, similarly, if x1, x2 are 1, 1, then we do get this clause is satisfied, and this clause is satisfied, and this clause is satisfied, but this clause is not satisfied. Okay, so because we have one false here, even though the rest of these are true, the and of these all together would be false. Okay, simple as that. So that's an issue. Okay, so of course this is with two variables, but how many clauses would you need in order to get a SAT formula that's not satisfiable with three literals, let's say? That's a good question. Think about it for a second. Okay, you would need 8 clauses, right? Because you basically need to cover all possible options of the assignment. If you have to cover all possible options of the assignment, then it doesn't matter what the assignment is. You can't satisfy every clause. So if you have 3 literals, you would simply say x1 not, x2 not, x3 not, or and x1 not, or x2 not, or x3, and you would do this all the way to x1 or x2 or x3. All right? Makes sense? Okay. So the 3 SAT problem. Given a CNF formula, is there a truth assignment to the variable such that it evaluates the true? Yeah, we went over that. Okay. So, why is it important? SAT and 3-SAT are the basic constraint satisfaction problems, and many different problems can be reduced to SAT because of the simple yet powerful logical constraints. It arises very naturally in a lot of hardware software verifications, and it is a fundamental problem in the theory of NP completeness. Okay? But really, why this problem is important is because Cook-Levin made it important. And we're going to get to that in just a moment. So as we know, 3-SAT and SAT are technically different because 3-SAT has exactly the number of logical expressions, and SAT only has 3-SAT has exactly 3 literals per clause, and SAT has any number of literals per clause. So could we show that are these two problems of equal hardness? That's the question I have for you. Are these two problems of equal hardness? Now remember, if we reduce one to the other, we want to show a reduction. So that if we want to reduce x to y, we have the input for x. We want to get an algorithm for x such that we have some reduction, and that we transform it into an instance of y, so that the algorithm for y could solve it and give a yes or no. Okay? So that's what the reduction does show. And so the reverse reduction that was pointed out, the 3-SAT reducing to SAT, this is trivial, right? This is trivial. An instance of 3-SAT, you could put that directly into SAT and solve it, right? SAT includes all possible CNF formulas, including the ones that have only 3 literals. So this reduction is trivial. You don't even need the reduction here. You could just connect IX directly to IY and put it into the SAT solver. Okay? So what does this show? It shows SAT is at least as hard as 3-SAT. Okay? So 3-SAT gives a bottom. So it shows that SAT is at least as hard as 3-SAT. Okay? In terms of computation. Okay? So now the question is, can you do the reverse? Right? Because the reduction for SAT to 3-SAT is more complex because 3-SAT is not going to take this formula. Right? 3-SAT is not going to be okay getting a non-3CNF formula into it. So you have to somehow transform this formula into a 3CNF formula, so that if this formula is satisfiable, then this formula is satisfiable. Okay? And if this formula is not satisfiable, then this formula is not satisfiable. So you have to start out with a CNF formula and get it to be a 3CNF formula. So basically you got to somehow change the clauses here, break them up or add stuff on so that you maintain the satisfiability of the equation, but each clause only has 3 literals. Okay? So how do we do it? So the good news is that this is possible. Okay? This is possible. And how do we do it? Well, first thing is we need to get this clause up to three literals, okay? And the easiest way for me is simply to repeat the literal. Not x or not x or not x. Okay? This is technically allowed. I've looked a lot in various textbooks. there's a controversy. I mean, I know there's going to be probably some computer science instructor or expert that tells me that I can't repeat literals in a clause. I have tried looking this up, and I can't find any good textbook that forbids repeating a literal in a clause. So if someone wants to correct me, I fully invite them. But until that moment, I think you could very easily get away with repeating the literal in the clause. And so anything that's less than 3 literals in the clause, you could simply pad it with an extra literal. Okay? So if this clause is satisfiable, if this clause evaluates to true, then this clause will also evaluate to true. If this clause does not evaluate to true, then this clause will not evaluate to true as well. Right? Okay, so we know how to handle that. Now we need to find a way to break longer clauses longer than 3, into a CNF formula. And so how do we do that? Into 3 literals. So how do we break up these longer clauses? So here's the trick. In these longer clauses, right, only one of these literals need to be true, right? So if we break it up, if for instance, we take this clause and transform it into X or Y or Z and W or U. The thing is, let's say the truth assignment for WXYZ, UWXYZ is X is 1, and then the rest are 0. Then in this case, this clause evaluates to true, and this clause evaluates to false, and the formula is no longer satisfiable. So if this clause is satisfiable, then this clause may be satisfiable, but it also may not be. Okay, so it's ruined something. So we want this. Always to be satisfiable, always to evaluate to true, if this can evaluate to true. So what do we do in this case? Well, we could very easily add in an extra variable. And actually, I'm going to just use my iPad here. Make some space. And I'm going to add in this extra variable, A or A not. Okay? So, what happens here? This A is not part of the original SAT expression, okay? But here's the thing. If this literal, let's say the assignment here was 1 0 0 0 0, okay? 1 0 0 0 0. This clause evaluates to true. And the thing is, if A is equal to 0 also, if this evaluates to true, then this clause could evaluate to true, and hence the whole thing will evaluate to true. Okay? So we'll just assign, so in this case, A could be assigned to 1, and this will be assigned to 0, and thus this clauses together will evaluate to true, mimicking that this clause evaluates to true. Okay? Now, you may be saying, but we're actually assigning a literal to A, we're actually changing the expression. But that's not important. If we can change the expression for the reduction. It doesn't matter if we change the expression or not. We just need to change the clause so that it's always satisfiable if the changed equation is always satisfiable if the original was satisfiable. And if the original was not satisfiable, let's say this was 0, then this would be 0. And what would happen? This, no matter what we assign A, okay? If we assign A to be 1, if we assign A to be 0, then this clause evaluates to true, and this clause evaluates to false, and therefore the whole thing evaluates to false. If we assign A to be 1, then this thing evaluates to false, and this thing evaluates to true, and therefore the whole thing evaluates to false still. Okay? So because we're having a literal and its complement sort of bridging two clauses, one of the clauses, this will take care of this will let one of the clauses be satisfied on its own, but then the other clause needs to have something that'll satisfy it. in the same way that it was satisfied in the original expression. Okay, so that's how you break longer clauses up into shorter clauses. And you could keep repeating this process. You'll have to repeat this process for 4 also in order to get clauses that are all of size 3. Hopefully that makes sense. So that's how the reduction works. So using this reduction, we can turn any SAT formula, any CNF formula, into a 3CNF formula. Okay, using this reduction here. Okay, and so because we could reduce any SAT formula into a 3SAT formula and then solve it using a 3SAT solver, then it means that SAT is reducible to 3SAT. And therefore, this means 3SAT is at least as hard as SAT. And we also knew from before, from 3SAT to SAT, that SAT is at least as hard as 3SAT. And therefore, we see that the two problems, 3SAT and SAT, are both have equal difficulty. Okay? So that's how you convert any problem, for any SAT problem, into a 3SAT problem. And that's why when people talk about SAT, they always are usually referring to 3SAT, because you could reduce any longer SAT formula. You could reduce 100 SAT into a 3SAT problem. Okay? And unfortunately, you can't go any smaller than that. You can't reduce a 3SAT problem into a SAT problem, because if you do this trick on 3 literals, if you try to break up this with using 3 literals, you end up with more 3SAT formulas also. Okay? So I'll leave that to you to verify on your own. But that's the SAT problem. So next, let's look at the larger space of NP, like P versus NP, and algorithmic complexity. Thanks.